In linear motion, the first thing we talked about was displacement, which is how far something has traveled. From there, we talked about velocity, which is how fast something is moving, and then acceleration, which was speeding up or slowing down. We're doing the same thing here in angular or rotational motion. We talked about in the previous tutorial angular displacement. It was still how far. It's just now how far it rotated. Now we're talking about angular velocity, which is still how fast. Velocity is still how fast. But now it's how fast something is rotating. That's the only difference. So these ideas are the same. Nothing is new. We're still talking about how fast, how far, speeding up, slowing down. We're just now applying it to rotation. All of those values were in linear motion vectors. So they're all vectors again, which means that they have a direction. Now in this case, up and to the right are not positive because we're rotating. Instead, counterclockwise is positive, according to the unit circle. When you did the unit circle in math class, 0, and then you went pi over 2, and then you did pi, and then 3 pi over 2, and then finally got back to one complete revolution, which was 2 pi radians. And so we're still, again, going counterclockwise is positive, same as in your math class. Clockwise is a negative value. And our symbols, well, we have omega for angular displacement. Now, if I were to write this in script, it kind of looks like a W with the curls just kind of bent inward. So that's omega. The units, instead of being meters per second, are going to be an angle divided by time. So radians per second, or perhaps radians per minute, or perhaps revolutions per minute, which we refer to as RPMs. That's a very common one to think of here. So again, the only difference here is now it is rotating. So we talk about how much angle, not how much distance in a given amount of time. Same thing with angular acceleration. Acceleration is how fast something speeds up or slows down, how much it speeds up or slows down. So again, we are moving faster or slower, but it's rotating faster or slower. Same as like a car tire. As you speed up the car, the tire rotates faster and faster and faster. It has an angular acceleration. It is a vector, which means it has a direction, same as regular acceleration. And again, counterclockwise is positive and clockwise is negative. Now the symbol here is the Greek letter alpha. I'll write it in script over here as well. Sometimes the font doesn't really look like the way I'll write it when I write it doing the problem. So alpha is the Greek letter we'll use for angular acceleration. That's what you're going to notice. We're going to use Greek letters when we're dealing with rotational motion to let us know that we're dealing with rotation. Usually English letters are linear motion and Greek letters are rotational motion. Now instead of being a meter per second squared, we're going to have an angle divided by a time squared. So we'd have something like a radian per second squared, the most common, revolution per second squared, or even a revolution per minute per second, as long as it's going to be an angle divided by a time again. To give us an idea of what this represents, let's say we have 5 radians per second squared, which is the same thing as writing 5 radians per second per second. This means that the angular velocity increases 5 radians per second every second. So if I start with 0 radians per second at time 0 seconds, after 1 second, I'm now moving at 5. After 2 seconds, I'm now moving at 10. And after 3 seconds, I'm now moving at 15. I increase my angular velocity by 5 every second. That's what that is representing. Now, looking at those equations, going back to the equations, you'll notice that the equations are no different than what we had before. Here's our equations from linear motion. The first equation was for constant motion, not speeding up or slowing down. Now all that we're doing, this looks kind of complex at first, but it's not. All that we're going to do is replace x's with thetas. Remember, these are both displacements. These are still both displacements. We're going to replace v's with omegas. These are still both velocities. And a's with alphas. They're still both accelerations. All you've got to do is memorize these conversions. So instead of v is x over t, we have omega is theta over time. It's still velocity equals displacement over time. Velocity equals displacement over time. Nothing is different. But again, that is for constant motion. It is not speeding up or slowing down. Same thing with the other equations. It's still final velocity equals initial velocity plus acceleration times the time. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. Displacement is equal to 1/2 the initial velocity plus the final velocity times the time. And final velocity squared equals initial velocity squared plus acceleration times displacement. All these equations are exactly the same because they are not new concepts. They're still the same idea, only now it's applying to rotation.